In any complex process, problems are often hiding right there in plain sight, just buried under mountains of data. Today, we're going to go on a little data hunt. We'll follow a real case study from a chemical plant and see how a few simple statistical tools can turn a whole sea of numbers into a really clear path to a solution.
So here's the big question, right? You are just flooded with data every single second from dozens of sensors. How in the world do you separate the signal from all the noise? More importantly, how do you pinpoint that one single variable that's throwing everything else off? Well, let's walk through how it's done. Okay, so let's set the scene. We're at a plant that produces a biopesticide called Thurasave 24. Now, the fermentation process, it's kind of like baking a very, very precise cake. To get a high-quality product every single time, certain key variables have to stay within really specific limits. And look, this isn't some story about a plant in crisis. This is about the normal, routine work of maintaining excellence. So these are the 4 vital signs we're going to be keeping an eye on. We've got pH, temperature, airflow, and agitation speed. Each one has a target range. You can think of it as a sweet spot where the process runs absolutely perfectly. Think of this as our map. These are the rules the process is supposed to be following. Our job as data detectives is to figure out if it actually is. So where does an investigation like this even begin? Well, it starts with a basic health check. Before we can even ask if the variables are on target, we first need to know if the data itself is, well, if it's behaving normally. So the very first step is to just look at the shape of the data, what statisticians call its distribution. Let's kick things off with pH. We're looking at 2 key metrics here, skewness and kurtosis. Now, you don't need to be a statistician, but the main thing to know is that for normal data, these values should fall somewhere between -2 and +2. And as you can see, pH is sitting comfortably right inside that range. So first check, passed. Okay, now take a look at the airflow data. Whoa, that's different. The skewness and kurtosis values are nearly -20 and over 61. That's miles outside our healthy range. This is a massive red flag. It's screaming at us that the airflow data is not behaving normally at all. Something is definitely up here. Okay, so let's just quickly recap what we've found so far. The pH data, it's behaving just like we'd expect. But the airflow data is showing some really significant statistical deviations. So this very first step has already given us a huge clue. Not all of our variables are acting the same way. All right, we've looked at the shape of the data. Now we get to ask the next logical question. Is the process actually hitting its targets on average? For this, we're going to pull out a really powerful tool called hypothesis testing. Basically, it helps us figure out if a little blip in the data is just random noise or if it's pointing to a real actual problem. So let's put temperature under the microscope. The target is 30 degrees. So our starting assumption, what we call the null hypothesis, is that the average is 30. But the data shows an average of 28.93. Now the key thing here, look at that p-value. It is tiny, practically 0. In statistics, a p-value that low gives us overwhelming evidence to reject our initial assumption. And that is the power of this kind of test. We can now say with a high degree of confidence that the process isn't just fluctuating randomly, it's consistently running cooler than its limit. We've just gone from, that looks a little low, to, yep, we can prove it's consistently running cooler than it should be. We found another solid clue. So we've identified a couple of potential issues now. But in the real world, you can't just fix everything all at once. You've got to focus your energy. And this is where something called Pareto analysis comes in. It's a fantastic tool for finding the vital few causes that are behind the majority of the problems. You've probably heard of the 80-20 rule, right? That 80% of the effects come from 20% of the causes? Well, this is it in action. This table breaks down every single time the process went out of its specified range. And just look at that count. Out of 61 total issues, pH was the culprit 48 times. Temperature was responsible for the other 13. And agitation and airflow? 0 incidents. Just let that number sink in for a second. Nearly 80%. Almost 4 out of every 5 problems in this entire process came from one single variable, pH. Folks, this is our smoking gun. We now know exactly where we need to focus our attention to get the biggest bang for our buck. And this, right here, this is our aha moment. The chart just makes it impossible to ignore. Sure, temperature is contributing a little bit, but pH is the overwhelming source of instability. All that data, all that analysis, it's all pointing to one thing.
Okay, so we've pinpointed the what. Now for the final and honestly the most critical step, understanding the why. The data tells us that pH is the problem, but it doesn't tell us what's physically causing the pH to be so unstable. Now it's time to go from the numbers on the screen to the nuts and bolts in the real world. So to find that why, the engineers used something called a cause and effect diagram, which you might know as a fishbone diagram. It's this really cool structured way to brainstorm everything that could possibly be causing the problem, looking at the machinery, the methods, the materials, even the people, to trace that issue all the way back to its single root. And here it is, the final diagnosis. The root cause wasn't some complex chemical reaction or a mistake in the procedure. It was a simple physical fault. The fermenter wasn't properly airtight. A small leak was causing that major pH instability. And that's the whole point, right? We started with all this abstract data, and we ended up with a physical, real-world thing that they could actually go and fix. So let's just recap the pathway we followed. It's a really logical flow. We started with a normality test to check the data's basic shape. Then we used a hypothesis test to see if it was hitting the target. After that, Pareto analysis helped us prioritize the biggest problem. And finally, that focus led us straight to the root cause. It's a simple, powerful, and totally repeatable framework. And this, for me, is the biggest takeaway from all of this. The goal here was never about finding fault or pointing fingers. It's all about continuous improvement. Statistical analysis isn't a tool for placing blame. It's an instrument for finding clear, data-backed opportunities to just make things better. So here's the bottom line. Every process, whether it's in a factory, a software company, or even just your own workflow, it's all generating data. And hidden inside that data are clues to make it more efficient, more reliable, and better. So the only question left is, what opportunities are hiding in your data?